Good morning, ma. Am I audible, ma?
Yes, sir.
Okay. Screen visible, right?
Yeah, it's visible.
We'll wait for some 2 minutes so that other people join. Okay, 20 people are there. Shall we start, ma? Already it's 5 minutes. Yes. Ma, shall we start? Okay, let the people join. It's 28 now, including me. So we'll start the presentation. Yesterday we are discussing about the how to write the rate equation for the adsorption, desorption, and surface reactions, right? So here, whatever I'm giving here, it is just cut and pasted from the book. In between, the steps are not there. We'll go first in this, and then I'll show you a detailed calculations bit later, right? So the net rate of adsorption of a component A, how much component, this already we discussed yesterday, I'm just repeating it. So this is the Cm is the concentration of the monolayer minus concentration of this. So this is the driving force. This is the coefficient, that is constant, into Cm. This is for the adsorption. I am writing for a net rate. So net rate in the sense how much is adsorbed minus how much is desorbed. This is the desorbed. Ka and Ka star is a constant. Ka is for the forward reaction. Ka star is for the reverse reaction. So we can take out Ka outside. If I take out Ka outside, this becomes Ka star divided by Ka. I can write here. If I take this common outside, I can put this Ka here, and then I can take out like this, right? Now this thing I'm taking as Ka by Ka star, let it be capital Ka. Then what will happen? This is the reverse which is having Ka by Ka star is Ka, equilibrium constant, but here it is Ka star divided by Ka, therefore 1 by Ka, right? So Ka I can take it out, small Ka. I can write like this. Now here Cm minus C star is nothing but the vacant site. I can write if only A is absorbed. If a gas consists of only A, then you can write C instead of C, Ca. But if the gas consists of A, B, C, then you cannot write C is Ca because C is a combination of Ca, Cb and Cc. So if only A is adsorbed, then C you can write as Ca. Then this particular thing can be written as Cv, that is what vacant site. So Cv star is the concentration of the vacant site. Ca is the concentration of A in a gas phase. So Ra is Ka, Ca into Cv, because this I'm writing as Cv. Cv minus 1 by Ka, capital Ka, Ca star, right? So this Ka is the intrinsic adsorption rate, is large with respect to the other steps in the overall conversion process. Here you are using it is rate of adsorption. Only for rate of adsorption you are writing. So we discussed that the net rate of adsorption equals 0. Then your Ca equilibrium will be equal to this particular thing. That is Ka, Ca, that is the concentration of A into the concentration of the active site, where K, capital Ka is the adsorption equilibrium. Like that, here we are discussing only about A plus B gives a product. If it is A2 plus 2x, x is nothing but active site. If it is giving like this, then also you can write here. You can see this A is giving you product. Therefore, into Cv you are getting. If there is two active sites, then Cv square will come, right? So how much based on this particular equation, you can write the final form of that equation. So rate of desorption also it's like that C dot X, because this is the product which is formed. Now it should be desorbed to C, that is the product, into the active site, whatever it is there. So this also, if you go with the same thing, again the net rate of desorption will be the forward reaction minus the reverse reaction. So you can write like this. You can write like this. Then again, if you take KD common, because KD is common, then minus KD, because this is minus is there. So you want this to be coming as the first. Therefore, if you take minus KD common, this term minus this term, again KD divided by KD star, you can put as a capital KC, and then you can do it. If there is a surface reaction controlling the third one, then either A plus B is giving you C, either A can sit on the active side and interact with B to give you C dot X, or A is interacting with B which is in the active side, then also you can get like this, or A is sitting on an active side and B is also sitting on an active side to give you C dot X. Anything it can come, anything it can go. So based on that, your expressions will change. Whatever equation, based on that, your final form will change. If this is the equation, we know how to write it. We know how to write this particular thing, right? So again, if you're writing the surface reaction net rate, this is the forward reaction, this is the backward reaction, then Ks, S is the surface, right? So here D is the D. Yeah, please unmute yourself, some of you. Yeah, thank you. So KD, we are giving some suffixes in such a way that the D tells you it is desorption, A tells you it is adsorption, and S tells you it is reaction. So you take out K's common side, then K's star K's dash divided by K's, you put as capital K's, right? So if this is like this, then you are getting this. What are the reactants? A into CV minus 1 by C into what is the product you are getting, right? So like that, if like this also it can be. That is A is sitting on the active site and B is sitting on the active site to give you C, which is sitting on the active site, the product, and it left out one active site. You can do this also. You can get the expressions, right? Here, one important thing is how to get the final form of the equation. So here it will look very clumsy. Let us go to the nodes and then come back to this. Okay. I'll go to the nodes now because this will give you a detailed explanation rather compared to that of the nodes. Hope it is visible for all the people. Yeah. Is it visible, ma? All the people? My nodes is visible. Yeah, I think it is visible. So this kind of things is called as Langmuir-Hirshelwood kinetics, LH kinetics, or Haugen-Watson HW kinetics. So we'll see what is this. Yesterday we discussed about Langmuir isotherm, how to write it. So you are getting theta is equal to Kp play by 1 plus Kp. K is the equilibrium constant, P is the partial pressure. You can write that theta as V by Vm, that is the volume of the site divided by the volume of the monolayer, volume of the gas absorbed divided by the volume of the gas which is absorbed in a complete monolayer, right? So you can write in terms of concentrations also. When you are writing in terms of concentration, your driving force also should be in terms of concentration. You can write theta is like this, Kc into Cg divided by 1 plus Kcg, right? Cg is the gas concentration. So here, when we want to discuss about these kinetic models, there are three steps which will come into picture: adsorption, reaction, and desorption. That is, the gas is adsorbed on the surface. Then on the surface, there is a reaction. And from the reaction, the products will be desorbed from the solid. So for these three things, you have to write the rate expressions. And if one particular thing is controlling, then your what you call global or overall rate, you have to write in terms of only that particular thing. For getting this, what Haugen and Watson followed is like this. You see, let us designate the total concentration of the active site, active catalytic site as S0. So he is telling that there are some active sites on the catalyst. Let the total active sites, let it be S0, right? So the notations may be different than the material what I am giving here and even in the PowerPoint. But finally, the crux of the what do you call the final expression is going to be the same. Okay. So let S naught be the total active sites, a constant for a given catalyst. So for a given catalyst, any catalyst, S naught is going to be a constant. So this S naught will be a combination of different things. One is S. S is nothing but the occupied by various species. So S is that volume or whatever it is that is occupied by various adsorbent species. The adsorbent species can be SA, SB, SC. That is, a gas is having a combination of A, B, C, right? So S naught is S plus SA plus SB plus SC. So let us assume that we have a relation. What is the equation which we are having? Let us assume A is a gas, B is a gas. On a catalyst, it is giving you C gas and D gas. This is the reaction which is happening. Let us assume this reaction. So we imagine that the reaction is taking place in steps. When A is a gas, B is a gas, both these reactants are sitting on a catalyst surface to give you C and D. So how this reaction is happening? We are just imagining in a series of steps. What could have been the steps? A will be sitting on the active side and reacting to give some intermediate. and B is also sitting on the active side to give you some intermediate. This intermediate and this intermediate is giving you some intermediate product. That intermediate product is dissolved to give you the C and D. So that is how we will assume it is in a series of steps. So now you see the series of steps. Now the equation is A plus B gives C plus D. All are in gas phase. Only the catalyst is in solid. That is the adsorbent. So A is sitting on an active side. In the PPT, I gave X. Here I'm putting as yes. Yes is the active side, whatever it is. Yes. Yes is the concentration of the active side. So A is the concentration of a gas. A is sitting on active side to give you some intermediate. A is, yeah. What happened? Ended out. Okay. This is equilibrium reaction, reversible reaction. Let it is K1. This is K1 star. Okay. This is the first reaction. The second reaction is again, there is one more component B. Again, I'm telling you, don't get confused. How we are getting this particular thing, expressions, he will give you directly here. I'm ready. So how I'm getting this, I'm giving in a detailed form here, right? So some of you, those who joined recently, you might be wondering what I'm doing. I'm just doing here. How I'm getting these expressions directly, I'm writing these expressions. A lot of steps are there. How to write that expression, I'm showing you in this. Okay. So A plus S, this is one reactant which is sitting on the active side to give you some intermediate. This intermediate is highly unstable. So both forward reaction and backward reaction. Backward reaction, we always put a star dash. So K1, K1 dash. Like that, there is one more reactant B, which is sitting on the active side to give you BS. Again, K2, K2 star. So what are these two reactions? First two reactions are called as the adsorption reaction because the reactants A and B are sitting on the active side to give you some intermediates. Now what is happening? This intermediate, which is on the active on the surface, will react together to give you some intermediates. That is what here. AS, this is intermediate. I'm writing in bracket to differentiate that it is intermediate, and BS. Again, this is the third reaction. That is why I'm putting K3, K3 star, CS and DS. This is the surface reaction, right? This is the equation for the surface reaction. That is the same thing I'm putting here. Yeah, you can see A X is A dot X, B plus X is B dot X. This is what the adsorption steps. Instead of X, I'm putting as yes. Okay. Then in this particular thing, I'm putting AX plus BX. So here I'm putting as AS plus BS. Again, some intermediate, right? Don't get confused there. Now, what is happening? This intermediates should be dissolved to give you the product, right? So next step is this intermediate CS is giving you, there is no plus here, it is giving you C plus S, again K4, K4 dash, like the DS is giving you D plus S, therefore K5 and K5 dash. So these two steps are called as desorption, first two steps are called as adsorption, and third step is called as reaction. So what we did is this reaction, A gas plus B gas is giving you C gas plus D gas. We are assuming this particular thing is occurring in a series of steps. That series of steps, we wrote some different equations. So 5 equations we are writing. Each one is a reversible process. Therefore, you are giving the rate constants according to it. Right? So first two steps are the adsorption, second step, third step is the reaction, last two steps are the desorption. Out of these three steps, only one will be controlling the reaction. If there is one controlling, because if you club all the three, then it comes as a very big equations. So what we do in general analysis is we assume one is rate controlling. Based on that, you'll write the global rate. For any type of catalytic surface, we do the same thing. So how to know what step is controlling? This is a very important step. I can tell adsorption is controlling, reaction is controlling, desorption is controlling. But how do we know? We do from experiment. We do experiment and get from the experiment. We do experiment, and that experimental results will be fitted into the models to tell which is controlling, right? So some of you can ask, some of in the interviews also they can ask you how you can know that that particular step is rate controlling. Without doing an experiment, you can never tell which is controlling. Okay, that is one important question, right? So this is how you try to write your notes, because this notes is my MTech notes which I studied in IIT Madras, right? So our professor Dr. K. Krishnaya is a gem in CRE. I'm fortunate to listen to his 2 lectures of CRE, CRE1 and CRE2. Excellent, he will teach. He will teach you not only from the book, even outside the book also he will teach you. Like this, some questions he will ask, he will trigger your mind in his class. If you are having a time, you look at his NPTEL videos, is K. Krishnaya, is a gem of professor. You will be very interested to see. He takes the subject from the basics, right? So he writes on the board, not like a PowerPoint or something like that. So it is better if you can see his videos and write your own notes, right? So this is the regular class which we attended in IIT Madras. That time I wrote, right? So whatever I put something like this or some question mark, that means that he asked that question there. So I wrote that answer also there. Okay, whatever he tells. So next, now out of this 3 steps, we assume one is controlling. Let us assume surface reaction is controlling, right? So again, how to tell this surface reaction is controlling? You have to do an experiment and then fit the data to the kinetic models. Then only you can know. So what is the surface reaction controlling? Sorry, what is controlling surface reaction? If there is a surface reaction controlling, you have to take the surface reaction expression. That is what I'm taking. This is the sorry. This is the equation. Now, can I write the rate of disappearance? The rate of disappearance of any one of it is, this is the disappearance and this is the appearance. So K3, you know how to write the disappearance, right? So this is the disappearance in the sense K3 into AS into BS. This is the intermediate minus, this is the this side it comes. So K3 star into DS into DS, right? So you get like this. Now here we are assuming it is step 3 is reaction is controlling. When step 3 controls the reaction, all other steps are assumed to be in equilibrium, right? So we assume that the other particular adsorption steps are comparatively equilibrium, and what do you call, the other things are not much important. Only the resistance lies in the reaction. That is why we call it as the rate controlling. So other steps are very fast. Okay. So from this particular thing, from the step number 1, what is the step number 1? From the step number 1, that is the adsorption. How can we write this? This again, if you write, we can write AS by A dot S, right? Because this particular thing, you can write K1. Write the rate expression for the forward reaction, write the rate expression for the backward reaction. One over the other will give you K1. K1 is K1 divided by K1 star is equal to, how will you write K1? Forward reaction K1 into A, concentration of A into concentration of S. Like that, this backward reaction again, K1 star into concentration of this. Now, if you put one over the other, and if you put that as K1, then you can get AS by A dot S. Correct? Any doubt here? We can write like this. Correct? So like that, from the second step, we can write K2, which is capital K2, is the equilibrium constant. Again, it is BS divided by B dot S. The same way you write. Like that, from the fourth equation, again we get CS divided by C dot S is K4. Here it is the reverse because this is this side. Yeah, for earlier things, this intermediate is on the right side. Here it is on the left side. Therefore, you get ulta. K4 is K4 dash divided by K4. Whereas for this, K1 is K1 divided by K1 dash. It will be ulta, right? Just see. Like that, you can write for the DS, fifth step, K5 is K5 dash by K5. You right? Any doubt till now? Any doubt till now, man? No doubt. Now, can we write AS? We know what is AS, right? AS is nothing but from ninth equation, AS is nothing but K1 into A dot S. Like that, BS is nothing but K2 into B dot S. Like that, CS is nothing but K4 into C dot S. DS is nothing but K5 into D dot S. You substitute 9, 10, 11, 12 in 8. Then what will happen? Yeah, substitute 9 to 12 equations in equation number 8. Why we took equation number 8? Equation number 8 we took because we are assuming it is surface reaction is controlling. So we wrote the net rate of surface reaction disappearance. Then we are substituting this is intermediates, which we don't know. We have to write this intermediate concentration in terms of the knowns. That is why we are writing in terms of the knowns. Now, if you substitute AS, BS, CS, DS from 9 to 12, then what will happen? Minus R is equal to K3. AS is nothing but K1 into A into S. Like that, BS is nothing but K2 into B into S. So if you take it out, K1 and K2, CA into CB, S into S will become as S square. I'm taking out common because here also you get a S. That is why I'm taking out common. Like that, minus K3 star CS. CS is nothing but this. Again, K4 into CS. So I'm taking anyhow K1 and K2 common. Therefore, you have to put K1 and K2 down. Then only it gets cancelled out. So K1, K2 will be here. This will have only K4, K5, but divided by K3. That is the equilibrium. Into CS, CC into CD minus S square. S square because here S is there. Yeah, here one S is there. Here one S is there. Therefore, S square. Here also one S is there. Here also one S is there. Therefore, S square will come. Here equilibrium is nothing but K3 by K3 star. K equilibrium because you get K3, K3 star. So let us put some other capital. Now we have to eliminate this S square. S square is nothing but the active site concentration. How to eliminate this S square? S square can be eliminated from the equation. We know that S naught, that is the what do you call it? Total site concentration, active site concentration is S plus SA plus SB like that. Now what is SA? SA is nothing but the active site which is absorbed by A molecule, active site which is absorbed by B molecule. So we can write SA as one second. We can write SA as A dot S like that, SB as B dot S like that, SC as CS DS like that. So S naught is equal to S plus AS is nothing but now you see AS again you're substituting AS. AS is nothing but K1 into A dot S. That is what we are writing K2 like that. So from this, if I take S common because everywhere S is there. If I take S common, S is equal to S naught divided by 1 plus K1A, K2B, K4C, K5D. K3 won't come because K3 is what you are assuming it is rate controlling. So whatever is rate controlling, it won't come here. Correct. Now substitute this S here. Substitute this S here, right? That is what we will be doing. So otherwise we can write as S is equal to, we can simplify this S naught divided by S naught is nothing but the total active site concentration divided by 1 plus what are this A, B, C, D. A, B is nothing but the reactants. C and D is nothing but the products, right? So we can generalize that S by S naught. Now you see S by S naught. You write as S by S naught is nothing but a fraction. Am I right? So S naught is the total. S is the surface which is absorbed by the molecule. So we get a fraction. S by S naught is nothing but 1 divided by 1 plus what is this? This is all pluses. We can write sigma. We can write sigma Ki Xi. Ki Si or Xi, whatever you give, right? So this is the fraction of the vacant sites. Si S by S naught is nothing but the fraction of vacant site. That is nothing but theta. That is nothing but theta. Okay. Now substitute S by S naught, this equation, in equation number 13. This is the equation 16. You substitute this equation here in 13. Then you rearrange that equation to give you like this. R is equal to K3, K1, K2, S naught square. This particular thing you get. Now these are all constants because these are all constants. K1, K2, some equilibrium constant. You can make one more constant K naught, whatever constants you are having. Therefore, K CACB minus CCCD divided by K naught divided by 1 plus entire thing whole square. This is the final form of the equation. From this equation, what we can understand is, now what is the reaction? What is the reaction, ma? C A is sitting on an active site, B is sitting on an active site to give you C and D. C is sitting on active site and D is sitting on active site. So whatever is the reaction, whatever is the reactants, it will come first. Whatever is the product, it will come second. There will be a negative sign divided by 1 plus the sum of entire thing, whatever is there, into its coefficient whole square it will come. So this is the generalized form of the equation. So where K you are making as constant, you are making whatever case or K capital case or small case as one constant, right? So S naught square is also constant because it is the total active site. So whenever the reaction rate is controlling, this is the important things which you have to understand from the equation. Whenever the reaction is controlling, that will not be present in the numerator. So what is controlling? The reaction is controlling. Therefore, that particular term will not be present in the numerator. How many reactants are there? That many will be in the numerator. How many reactants are there? If there is A, B, C is the reactant, then Ca, Cb, Cc also will come. So how many reactants are there? That many will be in the numerator, and how many products are there? That many will be in the second term of the numerator. Again, one more. 6 constants are there. What are the constants? K, K0, K1, K2, K3, K4. This is K1, K2, K4, K5. K3 is not there because K3 is controlling. Whatever is controlling, that will not be in the denominator. That is what it will be given here also. One more. If there is some inerts present, if there is some instead of A, B, C, D, if there is some inerts also present in the gas, then that also will be should be added in the denominator. That is what. If the inerts are there, then we have to write Ki and Ci in the numerator. Here also will come and here also will come. Right. So you can see here the power is N. Whenever N, the number of molecules participating. Since 2 molecules are participating, this will be square. If there are 3 molecules participating, then this will be cube because you get S cube you get, right? So this whole power per N, that tells you how many reactants are participating, right? So this is the final form of the equation. Like this you can do for the other things also. Like this you can do for the other things. I'll just show that. Now this is the step. If there is a reaction like A gives R, A is giving R, there is only one reactant and one product. Again, if you write the steps, A plus S will give you AS will give you RS is giving you R plus S. So adsorption, surface reaction, and desorption. Now, if I think this for this reaction, the surface reaction is controlling, then straight away I can write, right, minus R is equal to capital K or whatever K into Ca. This is the which side it is coming, Ca, minus what is the product, Cr, divided by K naught, that equilibrium constant, divided by 1 plus what things are there, K1. There are two things, K1 Ca and K3 Cr. Whole power only one, because only one reactant is there. Understand? So like this, any number of reactions, you can write the generalized form. Now for suppose, if there is some adsorption which is controlling, if for this reaction, let us assume adsorption is the what do you call, rate controlling step, then still we can write again adsorption in the sense this reaction, first reaction, you write rate of adsorption is equal to K1 AS minus K star AS, A dot S. This brackets I am writing, it is in intermediate. A dot S, Ca into Cs. C I am not writing here, right? So A and S will give you the concentration. That is what I mean. So from the step number 2, we are writing K2 is Rs by R into S. Like that from step 3, Rs by R into S is K3. The same way as previous one we are doing. So you have to substitute what is AS and what is AS, and then substitute the equation. If there are some inerts present, then you have to write Ki is again Is by I into S. I is the inert and S is the active side. So here we are writing S naught is S plus SA plus SR, and we are assuming some inerts are present. So you have to write that. So S naught is SA you can write as A into S. SR you can write as R into S. SI you can write as I into S. Substitute that and then substitute read back into this particular equation. Then you can get the big form of the equation like this. Here you see, since adsorption is controlling, what is adsorption? Active site is there into A. So that is what is coming into minus this constants. Cr is the product which is coming divided by 1 plus Cr into Ki. Ki because it is some what do you call? You are assuming some inerts present, right? So this kind of reaction, this is the rate form for the adsorption control, right? Like that you can do for a desorption control also. Desorption in the sense you have to take this equation, then unknowns are there, Rs, we have to eliminate that unknowns in terms of the known and then write. That is what I think you will be doing in the next. So desorption also we can do the same way. So this is how the desorption will come. This is how the desorptions will come. What is this? This is the final form. So adsorption equation, desorption equation, surface reaction equation. If all the three are important, then you have to club all the three to give you the big equation. Understand? So since this equation is very big, that is why you make some assumptions that one particular thing is rate controlling. That means that the resistance offered in the other steps is comparatively negligible. Therefore, you eliminate it to give you the final form as very small quantity. So where this finds application, you can see here, this is the general forms of the equation. Any general form of the catalytic reaction, rate of a equation, how you write a kinetic term into the driving force term divided by the resistance term. This is how you write any rate of an equation. Kinetic term that is K, driving force that is nothing but Ca or something like that, divided by the resistance, right? So some industrial catalytic reactions, the rates of that using this particular Langmuir-Hirshelwood kinetics, what it came. Now this is the reaction H2 plus N2, ammonia. This is ammonia synthesis. H2 plus N2 gives you ammonia in presence of iron catalyst. So if you do an experiment and find out the rate will come like this. R partial pressure of N2, partial pressure of H2 power 1.5 divided by partial pressure of NH3 minus K partial pressure of NH3 divided by partial pressure of H2 1.5. This is a highly what do you call non-elementary reaction, because this is how you get the non-elementary reaction rate. How you get this rate? That is what till now we discussed. You have to write like this and then find out how to, what is rate controlling. Based on that, you have to write the rate. You understood now how we get the rate for a non-elementary reactions, especially if there is a catalyst and some different phases are there. So one more is SO2 oxidation over a vanadium pentoxide catalyst. This is used in H2SO4 production. Again, R for this particular thing is K. PO2, that is partial pressure of O2, partial pressure of SO2 divided by partial pressure of SO3 whole power 0.8 minus this particular thing. How we are getting this 0.8 and 0.2? You get this expression like this. Yeah, 1 second. You get the expressions like this and then draw the graph with the data, whatever it is present, and then try to fit the data to that particular thing to give you the different coefficients, right? So you know that least squares and all, right? So based on that, you'll get this constants. This is one more example like that. You can have n number of examples. NO to NO2, you will have a highly nonlinear term here. That A, B, C, all that coefficients is given here. Like that, one more is synthesis of ethyl acetate, ethyl chloride from ethylene and HCl for the production of ethyl acetate. Ethylene is reacted with HCl to give you ethylene chloride. The reaction rate is this. The rate of a reaction is this. Again, how to get the constants? By doing an experiment, right? So like that, you can have n number of examples. This is one more example, hydrogenation of CO2 to produce methane. Methane production, this is one more example on a catalyst. You get the rate like this, right? So now you understood how to write the rate, right? So this is the same thing now I will get here. So this is the adsorption, this is the surface reaction, this is the desorption. Overall reaction is A plus B giving you C. Now can we write if surface reaction is controlling? If surface reaction is controlling, this is controlling, right? If surface reaction is controlling, we can straight away write the rate. That is what he is writing here. Ks divided by Cm, we are writing in terms of monolayer. Ca, Cb, because two are coefficients, that is the reactant. These two are the products, that is nothing but, yeah, you can see here. C, this is the product, and you get one more, that is the vacant site, which is there. That is why Cb. That's all, right? The same way what we wrote. This is capital Ks, this is small ks. How we wrote this? That is what I showed you here. Understand? That is what I showed you here. So like that, we can substitute all that extra terms which we don't have. Ca bar, Cb bar. Already we are writing Ca bar is Ka Ca into Cv. That is what we substituted as the other 9 to 12 in 13 equation, right? These are the equations. You substitute Ca, Cb, Cc from this equation. You get a big equation now. And substitute Cm is this particular thing. That is what in this book by giving as S is equal to S naught, all that. So substitute this, and then Cv is equal to Cm divided by 1 plus all this. Final form of this equation is like this. The same thing you are getting. See, what is the reactant CaCb? What is the product CaC? And divided by this particular thing, whole power square, because there are two reactants. Understand? So the reactant, what you call final form of the equation is same, except there here I am using X, and in my book I am using S, right? So like that you can do for the adsorption or desorption also. If you do then adsorption and desorption, you are getting this is adsorption rate. Like that you can see this is the desorption rate. This is the desorption rate. right? So please go through this materials, try to derive these equations. These equations are very handful when there is highly nonlinear equations, and to write the rate for that particular nonlinear equations, especially heterogeneous equations. Okay. Yeah, any doubt? I know you'll have a number of doubts because I introduced you to too many of equations. Once you know how to write, you are writing in terms of unknowns. You have to eliminate that unknowns in terms of the knowns, right? So any if you are writing a big overall reaction as sum of these reactions, this overall reaction you are writing as a sum of individual reactions, you will get some unknown intermediates. That unknown intermediate should be eliminated. That is the main concept. So you eliminate it and then you will get the final form of the equation, and then in that you put one particular thing is controlling, then it will become as a very small. Okay, that is the crux of this Langmuir-Hinchelwood kinetics. Yeah, I gave some examples also, right? Yeah, any doubt from your end? Yeah, I'm open. Yeah, any doubt, ma? You're all sleeping, huh? No one is there with me. Are you there?
Yes, sir.
Yeah, I completed my part. Yeah, I take the attendance 47, including me. So 46 people are there. Yeah, yeah, you'll have lot of doubts. I know. Just take a paper, take a book, and I'll put this also in your LMS. First, go through this book material what I'm giving. Just rewrite the equations by looking at whatever I wrote, and then write without seeing, then become comfortable, then you go back to the derivations. Okay, this is the entire derivation, whereas here I am not doing the derivation. Okay, I am doing the derivation, but not doing intermediate steps. Okay, yeah, any doubts from your side, ma? Any doubt from your side? Yeah, if there is no doubts, then I'll stop sharing this. So all of you clear? So like that you can write for any reactions. If there is one reaction, only one term power 1 will come, right? You do for different things. You see Gawane book, he gave you some examples with the 3 reactants, 2 reactants and all. Just go through that Gawane book and try to be familiar with the derivation part. Okay. Okay, then I stop the sharing. Thank you. Vignesh, you took the attendance. Shall I? Yeah, other people can leave. Thank you.
Thank you, sir.